In this video, we're going to talk about transition elements and stereoisomers, optical isomers. Go through all the examples of stereoisomers, include cis-trans, and include those optical isomers that come from the cis isomer. So complexes, just a reminder, a complex is a transition metal bonded to one or more ligands, and the ligand is the ion or the molecule essentially that can donate that lone pair of electrons. You can see down here, lone pair of electrons to that transition metal ion, which is a central metal ion, forming that dative covalent bond, which is referred to in transition metals as a coordinate bond. So an example of this that we're going to show you here is just the nickel. So as I've done in previous videos, you can see that you draw out the octahedral complex with your two bonds going up and down and then going in or away from you, into the board or away from you, and then coming out of the board and towards you. That's the best way of doing it. So always drawing it, start with those, and then you can put the ligands on. So in this case, we've got a neutral compound called water, or a molecule called water. Okay, and you can see that every single time I put one on, the oxygen is bonded to the nickel because the oxygen is the one with the lone pair. So we've got here the molecule ion that can donate a lone pair. So it's got a lone pair on it, which is donating it into the central metal ion. Okay, so the O must come first. If you draw it with the H that's bonded to the nickel, you will get an incorrect answer. And then what we do is we do the overall charge. So the nickel starting off as 2+, all of these are neutral. So if you take all the neutral ligands and then the 2+ nickel, you have 2+ over all. Now stereoisomerism, just a reminder here, we have isomers that you've done hopefully previously in the course, and you've got structural isomers, and in the structural isomers we consider positional, functional group and chain, and they're the ones we do. Okay, and then we do stereoisomerism, and that splits into EZ and cis-trans, and that comes to EZ is alkenes, but we'll talk about cis-trans in other videos because you can do cis-trans in transition elements and complexes. Okay, but we're going to talk today about the optical side. Now, this optical side, okay, is really, really important, and we're going to do lots of drawings. But stereoisomerism is the molecules that have the same structural formula. It's in green because you must remember it. Okay, same structural formula, but different arrangement of atoms in space. So a definition that you need to remember. Now, like I said, we're going to focus on optical today, and optical has these things called enantiomers. Now enantiomers, and again definition that is required, non-superimposable mirror images, okay, and they're also called optical isomers. So that definition for an optical isomer, which is also called an enantiomer, is non-superimposable mirror image. Now, just a reminder of where you've come across optical isomers before. Another word for optical isomerism is chirality. So chirality stands for handedness, as in you have two hands, okay, and if you take those two hands and you put them together, they're mirror images, but they're non-superimposable because your thumbs don't overlap each other, so they're non-superimposable. Now, normally you recognise that through carbons, so carbons with 4 different groups attached, and here you have a picture of these 2 different enantiomers with 4 different groups attached. Now, we're going to move on to how this can be done with transition complexes. Now, with these complexes, we'll show you now how to draw them. But first, we're going to talk about bidentate ligands and how they can make transition metal complexes. So in order to draw optical isomers, enantiomers, non-superimposable mirror images, we've got to look at bidentate ligands because that will become involved. So a ligand that can form 2 coordinate bonds to one central metal ion. The 2 options you've got ethane 1,2-diamine, so 2 carbons, 2 amines, 2 carbons, 2 amines. Okay, and then what you have is these 2 amines at either end, and you've got the lone pairs, and that is where your coordinate bonds are. Okay, it's really important the coordinate bonds go to that lone pair. Ethane dioate comes from ethane dioic acid. And you can see here you've got the carbonyls of the ethanoic acid essentially, here, and then you've got the O- because the hydrogen, the proton has left. Now that's why it can be called C2O4 2-, okay, because we've got these two oxygens with two minuses on them, and there's one electron here from the hydrogen because it goes as H+, and one from the oxygen, and so we've got two lone pairs here, and that's where your coordinate bond must go to. Now, really important, exam tip, one coordinate bond per lone pair, therefore coordination number is 2. So if there's 3 of these, the coordination number is 6. And that's the one we're going to look at now. So a coordination number of 6, and just remind you of cis-trans complexes, because we can draw optical isomers from the cis version. So cis-trans isomers can be done through 2 monodentate and 2 bidentate, but we're going to do firstly 2 of one type of monodentate and 4 of another. So the 4 of another is the ammonia, and you can see the ammonia is here, and you've got a lone pair of electrons, and that's where the coordinate bond goes to and comes from. Okay, we're going to draw it out. First of all, as we've done in other videos, draw out the octahedral complex because it's a coordination number of 6. And then we put on our chlorides because they're the 2 that make it cis or trans. And you can see we've put them 90 degrees to each other. And then what we'll do is fill in the rest because there's 4 ammonias and they're all connected where the lone pair is. So that 90 degrees is cis, so 180 degrees is trans. Again, stop the video, draw it yourself to keep you focused within this video lesson. Now, if we have here, we've got the chlorides, top and bottom, and then the ammonia is there, and that's 180 degrees. And that's trans. So we've got our cis and we've got our trans, but what we're going to do is we're going to take our cis, okay, and that cis we can turn into an optical isomer. So all we have to do is try and keep it very simple, and there's not much to do, just keep it simple. So I'm going to do exactly the same as I've done before. I'm going to draw, there's my bond, there's my copper. Okay, there's my bond going out the bottom. And then draw my wedges and my dash, because it's an octahedral complex, so I always do this first before I draw the rest out. Okay, and then I start putting my ligands on. So the ligands, we've got 2 chlorides, and we just do a mirror image. So the easiest thing is to put the chlorines on where they would be first. So there's a chlorine. If we mirrored this, and sometimes people like to put a little line like that to say this is my mirror image. Okay, this one, if I flipped it 180 degrees, would be on the far side. So there's my chlorines. Now that's chloride ions, just to make sure. Okay, remember they're 2 minuses, which means the copper must be 2+ because it's neutral overall. Now, if that is the case, we then just put in all of the rest. And here is the key, the little tip, is put the element that is bonding with the copper, the one that has the lone pairs by it first. Don't put anything else in the molecule, just put that first. And then what you can do is just add everything in. So I'm just going to add my hydrogens. Okay, and there are my hydrogens. Okay, let's make that a bit clearer. There we go. Now, we've drawn all of that, and all we have to do is finish it off with brackets. Now, this has no charge, but we still put the brackets around it. Okay, and there you have your cis isomer, your optical isomer, okay, which is a non-superimposable mirror image, and I would recommend that you make this using mods in your lab, okay, at school, because you can actually physically put them on top of each other. But the really important thing, this is an exam tip, really, really important exam question that comes up all the time, okay, is this. You've got 2 monodentate and 4 monodentate, which means from there you can make cis. We've got cis. In the previous slide, we made trans. Okay, we made trans. But of the cis isomer, we've also made an optical isomer. So basically, that means we can make an optical isomer or an enantiomer. Okay, now that means the total here is going to be 3 isomers. And they're not just 3 isomers. Remember, that's stereo, that's stereo, that's stereo. So this is 3 stereo isomers. And because it's 3 stereoisomers, this is often an MCQ question. So they'll put this in front of you, or the next example we're going to show, and they'll say, well, how many stereoisomers can you make? And the answer is 3, a cis, a trans, and an optical isomer. So we're now going to move on to bidentate cis complexes and then move on to the optical version as well. So coordination number 6 again, octahedral, cis, trans, isomers we're going to do, but this time we're going to do the 2 monodentate and 2 bidentate. Now remember, we've got these 2 types. We have got ethane 1,2-diamine, which is this one over here, and then there's ethan di-O8, and then we've got all the lone pairs here, 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 and here. Okay, and they're the 2 which we're going to use. We're going to show, first of all, we're going to show you the ethane 1,2-diamine. Okay, and we're going to do that here. So again, starting off with this octahedral complex, just put the 2 that are going to be cis to each other. Okay, so we can see here we've got bidentate, that's 2 connections, so we can't make those cis to each other, so it's got to be the monodentate. So really important every time it's the monodentate, you make cis to each other, or trans. Okay, and then what you do is you put the elements in that you're going to bond with. So you can see we put the nitrogens in that we're going to bond with. Okay, and then we connected them with these 2 carbons. All we did, NN, dush, dush. That's it. Okay, and then this is where people often get it wrong, is don't forget your hydrogens. Now your hydrogens, is really important, cannot be where the bond is happening. The bond happens to the lone pair. So you can put it above or below, or to the side. Okay, and if that's the case, these are all neutral. The nickel is 2+, the overall is 2+. So you've got a cis isomer because you've got this 90 degrees here. Now, if we go to the trans, we need to put them 180 degrees to each other. And again, stop the video, draw it, see if you can do it. All right, and there is our waters. Now we could put H2O, H2O. I'm just showing you the different ways of doing it. Just make sure that O is bonded to the nickel because that's where the lone pair is. And then we've got our nitrogens, and then we're going to bond them in. Okay, so there we go. And then just put your hydrogens in, and don't forget your hydrogens and your overall charge. Now that is how you do your cis-trans. But remember, the cis has an optical isomer of it because we can draw 3 stereoisomers. So let's try and do it again. Now, stop the video, try and do it yourself and try and see whether you can do it. But I'll show you anyway. So we start again and we've got our nickel this time. Okay, and then we've got our bonds and we're going to draw all of our bonds. There we go. Okay, and there we go. There we go. Now, we're going to do the mirror image. So this OH2, remember the mirror image is down here. This OH2 would be here. Okay, so let's put our O, okay, because we're just mirroring that one, O and then H2O. Remember the oxygen has the lone pair. And then this one would go at the bottom here. Again, I can do this as H2O or OH2, it doesn't matter. Then, from that point, I do it again with the atoms that are going to bond. The atoms that are going to bond are the nitrogens. So all I do is put N, 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 N. And that's it. Now, I know they're joined by 2 carbons, so I'm going to draw it with skeletal, but you can just go CH2, CH2 if you want, so it doesn't matter. Okay, and I'm just doing skeletal because it's easier. All right, now again, that mirror image would be the other side. Okay, and this one, and that's all I'm doing. Okay, and I've done it in a simple and easy way. And then I just put my H's on, which don't forget they can go top and bottom. Doesn't matter, just not in the way of the bond. Okay, so I've put my H's all the way around. And there you go. There's your brackets. And don't forget your 2+ in the corner. Okay, and there's your 2+ in the corner. So what we've done is we've taken a bidentate ligand. Okay, we're 2 bidentate, 2 monodentate. We created the optical isomer. And remember, for this as well, you would have 3 stereoisomers. And that 3 stereoisomers would be cis, trans, and an optical isomer. Okay, so cis, trans, and an optical isomer. And this time, this example is with ethane 1,2-diamine. So we're now going to do our final example of 3 bidentate ligands to make a complex. Again, this is octahedral. Okay, the majority of the complexes you do in this course are going to be octahedral. And we go through different examples in different videos, but all your optical isomers are going to be, like I said, octahedral. So 3 bidentate ligands, and we're going to use this time the opportunity to the other one, which is ethane dioate, and the ethane dioate has those 2 lone pairs where the coordinate bonds are. Now it can be referred to as C2O42-, and we'll put that into the formula at the end. So let's do this, move this across, give ourselves plenty of space because this does take quite a lot of space. All right, and so what we do is, here we'll have, and we're going to use cobalt 3+. So I'm going to do cobalt. Let's just write it up here. So we're going to do a cobalt 3+. So this cobalt 3+, again, we're just going to do it as the octahedral. Okay. Okay, and there we have it, our octahedral. Now, if that is the case, we're going to turn this into our complex, and we do it in a really simple way. It looks really complicated, but it's not. It's quite simple if you do it the way I do it. So, if you look over here, you'll see that the bonds happen where the lone pairs are, and they're always through an oxygen. So what I can do is I can just go, right, let's put an O, 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 and finally O. Okay, so we've got all those on. We then follow it through, and we can go 1, 2. So it's 2 carbons in between. It doesn't matter how you do it because you're drawing 2 optical isomers. Okay, and they'll only ever ask you to do that. So you just basically connect them up. So I'm going to connect up through 2 carbons, connect it up through 2 carbons, connect it up through 2 carbons. So now I've done this here. Now I've not completed it. I've still got the double bond O's, which I have not drawn, and they come off each carbon. So I just take each carbon and I do a double bond O. Okay, and we're almost done. Starting to look complicated, quite beautiful in a geeky kind of chemistry way. So basically, if you look at this, brilliant, and it wasn't that complicated. All we have to do is then put a bracket around it, and then we have to say, right, okay, that's 3+. So this central one is 3+. All of those are 2-, and there's 3 of them, so that's 6-. 6-, 3+, overall it is 3-. Okay, and that is your first one. We then do a mirror image to finish our optical isomers. All right, and then you need to give yourself plenty of space because these are big. Okay, then we do our cobalt again, and we start drawing our complex again. There you go. And we've done it. Then go to your nice pink colour, O's, 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 and more O's. Okay, so we've got all of those. We connect them via the 2 carbons, but this time we've got to do the mirror image. Okay, so mirror image like that. Just flipping it like this. That means this group here will be here. Okay, that group there will be up here. And then the other group will be down there. Start to see this drawing coming out now, okay? Then we put a double bond O's on, like we did before. Okay, there we go. Ta-da, ta-da, ta-da. Right, okay. Looks really complicated, but actually it was really simple if you followed this process. Right, and then all we do is bang, And there's your brackets. And we know it's 3 minus, so we're going to put 3 minus on there. Okay, really, it looks really common. Let's find a gap for me here. Right, okay, right. So you've got 2 optical isomers, enantiomers, non-superimposable mirror images. Again, make the molymods in class. See if you can flip them over. Okay, so from a bidentate, 3 bidentate ligands connected to a central complex, you're going to get 2 stereoisomers, and they're non-superimposable mirror images of one another. And that is how you can draw these enantiomers for these very, very beautiful complexes.